This video discusses the hazard of outdoor conveyor belt fires and the benefit of sprinkler protection to minimize the impact of these fires at client facilities. Fires in conveyors occur at a relatively high frequency. The most common ignition sources for conveyor belt fires have been identified as bearing failure, friction due to stalled idlers, or material buildup under and around the conveyor belt system, and hot work. Often the conveyor belt itself consists of enough combustible material to lead to a significant fire. If the material being transported or the conveyor housing is combustible, the hazard is increased. As shown in these images, some of these fires are very dramatic, causing large amounts of property damage and interrupting critical operations. Belt conveyors can be located outdoors, be miles or kilometers long, and have significant inclines. Each of these conditions pose unique challenges for fire protection for these conveyors. FO Research conducted a series of large-scale fire tests to better understand the hazard of outdoor conveyor belt fires and how to adequately protect the conveyors from significant damage. For background, conveyor belts are typically constructed of three main components: the carcass, the skim, and the covers as seen in the figure. The carcass is the reinforcement of the belt and provides the load strength, impact absorption, and stiffness. The skim is the layers of material that act like the glue and hold everything together. The cover protects the carcass. Conveyor belts are generally referred to as single-ply or multi-ply, referring to the layers of the carcass. A two-ply belt is depicted in the figure. Most modern conveyor belts use polyester for the carcass layers, natural or synthetic rubber for the skim coats, and a PVC, rubber, or urethane cover material. Each of these layers contribute to the combustibility of a conveyor belt. FO Research constructed the conveyor test arrangement shown in the image. An 80-foot, 24-meter-long stationary three-ply conveyor belt with both a top and return belt was placed in a semi-enclosed structure. The belt is a sand-gravel type belt with a polyester carcass, rubber skim coat, and no fire retardants. A 30-degree incline angle was chosen to represent a maximum realistic incline from a fire spread standpoint. And we have ignition. A propane burner is ignited at the start of the test, representing an exposure fire. Pieces of the belt continue to drip down at the ignition location, and a light gray smoke is seen in both the location between the two belts as well as above the return belt and under the cover. Large quantities of dark gray smoke are coming out of the enclosure from about the 50-foot mark on, and flames can be seen at 5 minutes and 20 seconds. Damage to the bottom portion of the structure is seen, and decision has been made to terminate the test at 6 minutes. Without active sprinkler protection, this test was essentially a free burn of the conveyor belt. 5 minutes, 40 seconds after ignition shows, the test looked very similar to the real-life fire events shown earlier, demonstrating the fire growth in the inclined conveyor belt without sprinkler protection. The maximum 60-second average temperature in the conveyor structure reached 1,616 degrees Fahrenheit, 880 degrees Celsius, and structural deformation was observed at the termination of the test. In this test, sprinkler protection is installed on a simulated dry pipe sprinkler system, since outdoor belt conveyors can be subject to freezing temperatures requiring this type of system. The sprinklers are K8 or K115 at an operating pressure of 10 psi, 0.7 bar, on 20-foot, 6.1 meter spacing up the length of the conveyor. And we have ignition of the propane burner.
That should go. Take it in. Propane off.
The ignition and first few minutes of this test parallel the previously viewed test with regards to fire development.
It's turned on with heads 2, 3, and 4 active. 4 heads are active.
At 3 minutes, water is supplied to the simulated dry pipe system in response to 4 sprinkler activations. At 4 minutes after ignition, the 4 operating sprinklers have the fire under control after discharging water for approximately 1 minute. As you can see, over the next 20 seconds, the fire is essentially extinguished. 4 of the 5 provided sprinklers operated and extinguished the fire as shown 4 minutes and 20 seconds after ignition. The maximum average temperatures in the conveyor structure did not exceed 1,000 degrees Fahrenheit, 538 degrees Celsius, and no structural deformation was observed at the termination of the test. In a real-life situation, the conveyor belt would need to be repaired, but the conveyor structure would have experienced minimal damage. As shown in these fire test videos, outdoor belt conveyors can represent a severe fire hazard, causing significant physical damage to the conveyor and interrupting operations for weeks or even months. The provision of properly designed and installed sprinklers can promptly control, or in some cases, extinguish a fire in these belt conveyors.